Section: Introduction. In this section, we will discuss the challenges faced by diffusion models in image and video synthesis due to their slow iterative nature during inference. These models typically require multiple network evaluations to generate images from noise efficiently. To address this issue, researchers have been working on improving the speed of sampling in diffusion models through better sampling techniques and distilled models that can match the quality of the original models in fewer steps. Recent advancements in distillation techniques have focused on reducing the number of model evaluations to just one step, enabling real-time image synthesis. The current leading method for single-step synthesis is adversarial diffusion distillation, ADD, which uses a pre-trained feature extractor called DINOV2 to distill models into a single-step, real-time text-to-image model. However, ADD has limitations such as being restricted to a fixed resolution and lacking control over the discriminator's feedback levels. To overcome these limitations, we introduce Latent Adversarial Diffusion Distillation, LAD, which offers stable and scalable distillation of pre-trained diffusion transformer models up to the megapixel level. Unlike ADD, LAD leverages generative features of a pre-trained diffusion model instead of discriminative features, allowing for better control over discriminator features and avoiding the need for decoding to pixel space. This results in a simpler training setup and outperforms previous single-step approaches. By applying LAD to the text-to-image model Stable Diffusion 3, we create SD3 Turbo, a high-resolution multi-aspect image generator that matches the quality of its teacher model in just 4 sampling steps. Our work also includes a simplified distillation formulation, a study of LAD's scaling behavior, and demonstrations of its versatility in image editing and inpainting applications. We will make our code and model weights publicly available for further research and development. Section Summary. In this section, we introduce diffusion models that denoise Gaussian noise into data iteratively. The denoiser in diffusion models predicts the expected image given a noisy image, and our method focuses on the rectified flow formulation with specific parametrizations. We present Latent Adversarial Diffusion Distillation, LAD, a stable and scalable approach for distilling pre-trained diffusion transformer models up to the megapixel regime, offering simplified training setups and outperforming previous methods like ADD in single-step image synthesis. Section: Diffusion Distillation. In this section, we delve into the realm of diffusion distillation. We explore how the denoiser D can predict clean images with sharp details for small t values and approximate the mean of the data distribution for large t, leading to a complex nonlinear differential equation. To tackle this, we need to solve the equations with small steps, which means many evaluations of the network f_theta are required. However, in some cases like text-to-image generation, our main interest lies in the final clean image distribution at t equals 0, which can be achieved through various differential equations. Distillation techniques aim to learn simpler equations that yield the same distribution at t equals 0 but with more linear trajectories, allowing for larger step sizes and fewer evaluations of the network f_theta. One such technique is progressive distillation, which condenses 2 Euler steps into one, reducing the number of steps needed. However, it may accumulate errors and require multiple rounds of distillation for an efficient model. Another method, reflow, trains new models on synthetic data from older models, also facing error accumulation challenges. On the other hand, consistency distillation aims to distill models in a single stage without iterative steps, but it requires stable training processes and advanced techniques like distillation schedules and hyperparameter tuning. Recent advancements have enhanced both consistency distillation and progressive distillation methods. The most effective distillation methods for text-to-image tasks now involve adversarial training. For instance, Adversarial Diffusion Distillation, ADD, utilizes pre-trained feature extractors as discriminators, achieving performance comparable to strong diffusion models like SDXL in just 4 steps. Latent Adversarial Diffusion Distillation, LAD, simplifies the distillation process by operating solely in the latent space, eliminating the need to decode back to image space. This significantly reduces memory requirements compared to ADD, enabling efficient training of large models for high-resolution image synthesis. Section Summary. In this section, we explore the concept of diffusion distillation, where denoisers learn to predict clean images by approximating the mean of data distributions, leading to nonlinear differential equations. Various distillation techniques aim to simplify these equations for faster convergence, with methods like progressive distillation and consistency distillation offering different trade-offs in terms of stability and efficiency. The latest approach, Adversarial Diffusion Distillation, AD, leverages pre-trained feature extractors to distill large latent diffusion models efficiently, achieving state-of-the-art text-to-image synthesis performance in fewer steps compared to previous methods. Section: Experiments. In this section, we assess our method in a scenario where we start from pure noise inputs. To evaluate, we calculate the clip score on prompts from drawbench and party prompts. We train for 10K iterations using an MMDIT model with a depth of 24, around 2 billion parameters, as the default for the student, teacher, and data generator. The results in this section are generally of lower quality compared to our final larger model. We investigate different ways of setting up the logit normal distributions for the teacher noise. When we bias the distribution towards lower noise values, we notice a lack of overall coherence in the images, although textures and local patches appear realistic. On the other hand, biasing towards higher noise levels improves coherence, but excessively high noise levels can harm texture and fine details. We find that setting the parameters to m equals 1 and s equals 1 provides a good balance, and we stick with this choice for the rest of our work. We explore the impact of adjusting the parameters of the logit normal distribution for the teacher noise level. Increasing the noise level enhances overall coherence, but biasing towards very high noise levels can lead to a loss of fine details. We aim to answer whether using synthetic data improves the alignment between images and text compared to real data, and if an additional distillation loss L_distill is necessary. Training with synthetic data outperforms training with real data significantly. While a distillation loss helps when training with real data, it does not provide any advantage for synthetic data. Therefore, training on synthetic data can be effectively done using only an adversarial loss. We compare consistency distillation and latent distillation with distillation, LAD. LAD outperforms consistency distillation in terms of stability and performance. Consistency distillation may require extensive hyperparameter tuning. We are among the first to attempt latent consistency models, LCM, training on diffusion transformers, and there is potential for LCM to achieve impressive results with larger models. We analyze the scaling behavior of model size in terms of student, teacher, and data generator dimensions. Larger student models show superior performance, and this advantage is effectively transferred to their distilled versions. While teacher models and data quality contribute to improvements, their benefits plateau beyond certain thresholds. This suggests prioritizing larger student models while allowing for smaller teacher models to optimize resource allocation, especially under memory constraints. Section Summary. In this section, we evaluate our approach by starting from pure noise inputs and computing the clip score on prompts from drawbench and party prompts after training for 10K iterations using an MMDIT model. We observe that biasing the teacher noise distribution towards low noise values leads to missing global coherence, while biasing towards high noise levels improves coherence but can harm texture and fine details, with pi, t, m equals 1, s equals 1, being a solid choice. Additionally, training with synthetic data significantly outperforms real data for image-text alignment, and using an adversarial loss alone is effective for synthetic data training without the need for an additional distillation loss. Section: Direct Preference Optimization. In this section, we focus on optimizing our models to better align with human preferences. We use a technique called diffusion DPO, which is based on direct preference optimization, DPO, but tailored for diffusion models. To enhance our models, we incorporate learnable low-rank adaptation, LoRA, matrices with a rank of 256 into the teacher model. We then fine-tune this model for 3,000 iterations using the DPO objective. In the subsequent training phase, LAD, we utilize the fine-tuned DPO model for both student and teacher roles, as well as for data generation. Surprisingly, we discover that by reapplying the original DPO LoRa matrices, we can further enhance our LAD student model. This improved model achieves a 56% win rate in a human preference study compared to the initial LAD student model without DPO, evaluated at a single step. The human preference study follows specific procedures outlined in the paper. DPO proves to be even more effective in a multi-step setting, as demonstrated in qualitative examples provided. We then move on to comparing our approach with existing methods in text-to-image synthesis and image-to-image tasks. We employ a training strategy that involves using both full and partial noise inputs to enable multi-step inference. For multi-step inference, we utilize a flow consistency sampler across 4 discrete time steps. We found that the consistency sampler works well for 2- and 4-step inference. At higher resolutions, we emphasize the importance of an initial warm-up phase for training stability, adjusting noise levels accordingly. In text-to-image synthesis, we conduct user preference studies to evaluate image quality and prompt alignment. Our model, SD3 Turbo, outperforms all baselines in both aspects, especially when considering multiple steps. We also assess our model against various state-of-the-art text-to-image models, demonstrating comparable image quality to its teacher model but with significantly fewer steps. Furthermore, we extend our approach to image-to-image tasks such as instruction-guided image editing and image inpainting. By distilling the image-to-image models using the LAD method, we observe improved performance in tasks like style editing and object swaps. Our distilled models show promising results in terms of speed and effectiveness, although there may be some trade-offs in controllability. Section Summary. In this section, we introduce direct preference optimization, DPO, techniques to improve model alignment with human preferences. By incorporating learnable low-rank adaptation, LoRa, matrices into our models and fine-tuning them with DPO, we achieve significant enhancements in visual appeal and performance. Our approach, termed LAD, demonstrates superior results in text-to-image and image-to-image synthesis tasks, outperforming state-of-the-art models in terms of image quality and prompt alignment. Section: Limitations. In this section, we show that in our human preference study, the South Dakota 3 Turbo model maintains the quality of the teacher's image in just 4 steps. However, this comes at the cost of prompt alignment. This trade-off leads to common challenges in text-to-image synthesis, such as object duplication, merging, fine-grained spatial prompting, and issues with negation. These challenges highlight a key trade-off between model capacity, prompt alignment, and inference speed, which is an interesting area for future research. When evaluating the model's image editing abilities, we noticed a lack of control due to the fixed image and text guidance strengths. One potential solution could be adjusting these parameters during training and conditioning the model on them. Additionally, the model sometimes shows rigidity by sticking too closely to the input, making significant changes difficult. We would like to express our gratitude to Jonas Mumluller for integrating the synthesis and to Ahmad Mostak for their exceptional support in OpenAI research.